Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 10, Spectacle Lens Prism Effect and Vertex Distance. Now you can think of a convex or plus lens or a concave or minus lens as actually being composed of two prisms. The plus lens has the two prisms' bases touching each other at the optical center of the lens, and the concave lens has two prisms having the apex of each prism touching each other at the optical center of the lens. Now, when you look through an eyeglass lens, if you're not looking through the center, or if the eyeglasses are constructed so that the center is not in front of your pupil, by the way, you heard about the cross-eyed teacher who couldn't get her pupils to face in the same direction, but I digress. The distance from your pupil to the optical center of the lens, we call that h. It's measured in millimeters. And it's also called the decentration of the lens. If the center is not in front of your pupil, the lens has been decentered. F is the lens power. P is the prism power that you are looking through. And that's measured in prism diopters. And the important formula, which is called Prentice's rule, is prism power equals H times F. Now I'm going to draw a cross-section of an eyeball. The left is the cornea, the clear window that does most of the focusing of the light. There's actually a lens inside the eye that also contributes to the focusing of the light, and the lens can actually change its thickness to increase its focusing power. For our purposes, we'll assume the lens inside the eye and it's completely flat. So this eyeball is neither nearsighted nor farsighted. We say it has no refractive error, and therefore light from infinity is focused to a precise point on the retina, on the inner lining of the back of the eye. And we say that the far point of this eye is at infinity. That means that light from infinity is focused on the retina. So let's contrast this eye with an eye that's nearsighted. The technical term for nearsightedness is myopia. So again, we'll draw our eyeball with a cornea on the left and the retina on the right. And for a nearsighted eye, the reason we say nearsighted is because near objects are focused on the retina when the lens inside the eye is at rest. And that place is called the far point of this nearsighted eye. Now what we do for nearsightedness is we prescribe concave or minus lenses. And light from infinity diverges through that concave lens. And if we extend those diverging rays back, we find the secondary focal point of this lens, which coincides with the far point of the nearsighted eye. So we have a virtual image forming at that point, which becomes a virtual object for the eyeball, which then takes the light from that point and precisely focuses it on the retina, on the inner lining of the back of the eye. So let's look at the hyperopic or far-sighted eye now, with the cornea on the left and the retina on the right. Parallel rays would focus behind the retina if they could get there when the lens inside the eye is at rest. They don't actually get there because the retina is not transparent. But you see, they do not come to a point on the retina. There's a blurry area there. So what we do for hyperopic eyes is we prescribe convex or plus lenses, and that lens converges the light toward that far point of the eye. That's also the secondary focal point of the convex lens. And the eye uses that image as a virtual object and focuses the light to a precise point on the retina. If you wear contact lenses, you may have noticed that the contact lens power is different from your eyeglass power. It's particularly true if the power is greater than plus or minus 4 diopters. And the reason is that the cornea, where the contact lens sits, is a different distance from the secondary focal point of the eyeglass lens than the eyeglass lens is. And remember that the secondary focal point corresponds to the far point of the eye. And that difference in distances becomes more significant the stronger the lens is. So the distance from the back of the eyeglass lens to the cornea, we call that the vertex distance, this distance here. I've abbreviated it VD. That is not venereal disease. It is vertex distance. And there's the vertex distance for the hyperopic eye and the plus lens. Now for the minus lens, the secondary focal point is on the left side, and for the plus lens, the secondary focal point is on the right side. So there's a way of calculating the contact lens power given the spectacle lens power and the vertex distance. So we'll start with the minus lens in the myopic eye. You first calculate the focal length of the spectacle lens. The formula is F equals 1 over big F in diopters. You get an answer in meters, so you multiply times 1,000 to convert to millimeters. And now you have to add the vertex distance to the absolute value of the focal length. And you do that because the cornea is further away from F prime than the spectacle lens is. And then you convert to the contact lens power by dividing negative 1,000 by what you found in step 3. For the hyperopic eye and plus lens, steps 1 and 2 are the same. In step 3, you subtract the vertex distance from the focal length because the cornea is closer to F prime than the eyeglass lens is. And then you calculate the contact lens power by dividing 1,000 by what you found in step 3. Remember, when you look through a prism, the image is moved away from the base and toward the apex. So when you move a convex lens down, you're looking through a base-down prism in the upper half of the lens, and the image appears to move up. When you move the convex lens up, you're looking through a base-up prism in the bottom half of the lens, and the image appears to move down. So the image moves in the opposite direction that the lens moves. If you tried this with a concave lens, the image would then move in the same direction as you move the lens.